Hey, is this thing on? Think it's on. Okay, we'd like to start talking about pressure in a fluid, but before we get into that, maybe we should say something about what is a fluid. What's the difference between a fluid and a solid? And what is pressure? Well, we're going to leave what is pressure unanswered for just a little while, but talk about states of matter and what is a fluid. Well, what is a fluid is not a solid. What's a solid? A solid is a crystal structure here, like this piece of neon, where all the neon atoms are being held together by each other in some sort of electromagnetic bonding pattern, some sort of chemical interactions, holding them together. And in this crystal structure, we can see they're packed in nice and tight. So it will be hard to squeeze them any closer to each other, right? If I start trying to squeeze on this thing and press them into each other, these atoms they're packed together pretty much as tight as they would go, so they'll resist that. They'd also resist shear forces. That is, if I tried to push to the, say, if I tried to push to the right on the top and to the left on the bottom, up to some limit of the crystal structures able to support shear forces, it's going to resist that and not change its shape. So it's going to hold on to its shape when I apply forces to it and maintain its solid shape. Now, what's it? Okay, so here we have a neon solid. Go to a neon liquid. What's the difference? Well, is the density different? It's a little less dense, as we could see for neon liquid, although it's still packed pretty close together. Are the neighboring atoms bonded with each other? Well, they are a little bit. They don't have the solid bonds. The bonds are less strong. So that means that will it support shear forces if I push, say, to the right on the top and the left on the bottom? What will happen? It will smush, right? It will the liquid will deform under shear forces. Okay, so there's a liquid. What about a gas? Well, you can see, well, what's happening with a gas? Well, is there any bonding now between the atoms of the neon? No. Those bonds are basically completely broken right now. It's floating around and it's completely filling up its container. Will it support shear forces? No, absolutely not. If I push to the left on or to the right on the top and the left on the bottom, that thing's just going to smush around. It will be easily compressible because there's plenty of space between the atoms, and so now what's a liquid? Okay, well, that's a liquid. What's a gas? That's a gas. What's a fluid? Well, it turns out a fluid is both the liquid and the gas. Okay, let me say a little bit more about what we've been talking about. Okay, so here we have a solid. So how's a solid going to work? Let's say I put a, I got to get over here. Here's the background. What if I put a force on a solid? Say, put some force like that on it. What will happen? And then maybe force it like this. And put some force here and a force here. What will happen to the solid? Well, it'll keep its shape, right? As long as I don't force it too hard. So that's great. It keeps its shape. What if I try to, compress it, say, push down on it. I would just say with some pressure. Won't worry about what pressure is, but it's a kind of force. It's like force. I push down on it, what will happen? Well, it won't compress. It's incompressible, right? The molecules are already packed as close together as they can be, so it's going to stay uh, constant density, right? Well, what is density? May have some idea. I say constant density. Seems fine. What's density? Density is mass per volume. And here for a solid, that's constant, right? Constant. So say for a given mass, so since this is constant, say if I have a fixed mass, if the mass is constant, then the volume also has to be constant. So for a certain amount of mass is going to occupy that certain amount of volume that goes with that mass. So we see how that works. Okay, and so this is for a solid. Now what's a fluid? Fluid we could see is either a liquid or a gas. Okay, so if we have a liquid, what's the story there? If I put force like that on the liquid and force like this on the liquid, say down here, what will happen? Well, it's going to shear, right? It's just going to smush around. So it won't resist shear forces. That'll smush around in that case. What about if I try to make it more dense by putting some pressure on it right here, like we did over here? So here's pressure here. I'm not worrying too much about what the difference between force and pressure is yet. But you say I'm trying to squeeze it now. More effectively, pressure will squeeze it. What will it do? Well, basically, you can't squeeze it anymore. It's pretty much incompressible here because it's a fluid. See, the atoms are basically already as close together as they want to be. Will it take the shape of its container? Definitely. Does it have to? I mean, if we look over back again, let me go over to this other view here. I'll get my mouse to work. So I got this other view here and grabbing that guy. There it is. Let's see. What are we talking about? A liquid. You notice this liquid, is it filling the container? Not exactly, right? Why not? Well, this is actually a very small amount of liquid. You couldn't even see this little of liquid if this was a real life sample of liquid, right? Because for any normal drop of liquid that you're used to seeing, how many molecules are going to be in that guy? A lot. I mean, like Avogadro's number, something like 6.23 times 10 to the 23 molecules per macroscopic blob of sample that you could see. Right? That's not this. This is a handful of molecules. You need a microscope to see this. So this is and so it's just a little tiny drop, clinging for its life in the bottom of the container, if you like. Right? And it's a cartoon molecule sample. Okay. Back to the other picture. Back to the other picture, and I guess we're almost done now talking about this. So now we know that a fluid, right, is both a liquid and a gas. Neither will resist shear forces. This one's basically constant density, takes a container shape. If there's enough of it, right, it will just fill the container, just as you might expect. This one over here, will this support shear forces like this? So if I put force here and here, say I'm getting tired of drawing these arrows, but you can see the gas is not going to resist that, right? It's just going to slosh around in a container, filling the container. Now, compressible, right? What if I do get my stylus, see if I can get my hand to do something here. Make a pressure right there. So let's say it was pressure, right? Was that, well, just let's say it's squeezing the gas into a smaller volume. That's going to be a pressure. Will this gas go for that? Yes, it will. Check. It's easily compressible. It means it easily changes its density, right? So over here, the density was constant, pretty much like a solid. But here, the density is probably not constant. Not in general, right? And generally not constant. Could easily be changed if I um, reduce the volume of the container or squeeze it with the pressure. Okay, well, we're just about done with this discussion now. I'm just going to wrap this up. We got to wrap it up here. We can wrap it up. Maybe just talk about a little difference of water. Water's pretty important stuff, right? I mean, we can thank life on Earth for the miraculous properties of water. Here's a sample of liquid water. Okay, with liquid water, you notice it's dense packed right now. Liquid water has got constant density because the water molecules, are as close together as they want to be right now. Okay, well, I can make water into a gas for sure. You can have water vapor. Okay, and now the bonds, the liquid bonds between the water molecules are broken. It's free form, filling its container, just like any other gas. Okay, we'll go back to a liquid. Right now, they're huddling together. Are they going to support shear forces, liquid water? Definitely not. Will they support pressure forces, compression forces? Definitely. This is not going to want to change its density. It's going to be a constant density. What about solid water? Now, what about what's happened to the density of this? Is the density of this less than or more than the liquid? Actually, you might be able to see right here the density of solid water is less, owing to its crystal structure. That's pretty darn important. That's the reason why ice cubes float, my friends. And if ice cubes didn't float, well, what would we have? I mean, we would have ice at the bottom of the ocean and we wouldn't have life as we know it. That's one thing for sure. So this is a very important property of water, that it forms this crystal structure which is less dense than it freezes in the liquid state. Right. And is that a normal thing? No, definitely not. For neon, if you go to neon solid, that's going to be more dense, a little bit more dense than the liquid. Yeah, you can see that. And same here probably for oxygen. You go to liquid oxygen, you go to the solid, that's more dense than the liquid. And so for most substances, here we go, argon, the solid is the most dense form, more dense than the liquid. And certainly the gas, well, that has a variable density. So the density of the gas is it's a property, but it's not a constant property of the substance. Okay, well, I think we answered the question. Maybe more long-winded than we should have. Catch you on the next video.